Every time you brew a cup of coffee, tap a glass screen, or draw a breath of air, you are interacting with chemical processes that go largely unnoticed. We move through our daily routines relying on a specific set of rules that keep our physical world functioning as expected. Consider the difference between a diamond and a common pencil. One costs millions of dollars, while the other is a disposable tool for homework. Yet both are made of the exact same element, carbon. The difference lies entirely in the geometry. Inside a diamond, every carbon atom is locked together with 4 neighbors to create a rigid, interlocking lattice. In graphite, those same atoms form flat layers that slide over one another, allowing tiny flakes of carbon to rub off onto your paper. This principle of elemental utility scales up significantly inside the technology we carry every day. To build a modern smartphone, engineers must coordinate over 60 different chemical elements to work in a single pocket-sized device. This silicon wafer, shown here with its etched grid of processors, serves as the physical foundation for modern computing. Beyond silicon, your phone requires copper for its circuits and a variety of rare earth elements to make the display function. Our assumptions about materials often lead to myths, like the idea that old window glass is thicker at the bottom because it flows like a liquid over centuries. In reality, glass is an amorphous solid. Its atoms are frozen in a random, non-crystalline arrangement that scientific measurements show does not shift on a human timescale. The physical properties we observe on the surface, hardness, transparency, or conductivity, are actually the outward signatures of how these invisible elements are organized. While most substances in the universe shrink and become denser as they freeze, water does the opposite. As it turns to ice, it expands. As liquid water cools, hydrogen bonds pull the molecules into a rigid, spaced-out structure. This hexagonal lattice creates more empty space than the liquid form, making the solid ice lighter than the water around it. This expansion allows ice to float. If ice were denser than liquid water, lakes and oceans would freeze from the bottom up, effectively eliminating the habitats where aquatic life survived through prehistoric winters. Other elements follow different rules to survive. Gold is remarkably stable because its atoms hold on to their electrons with enough force to resist reacting with oxygen. This chemical stubbornness is why gold artifacts remain bright and uncorroded after thousands of years underground. Even fire is a product of specific atomic behavior. A flame is a mixture of gases and particles where electrons are absorbing heat and then releasing it as visible light. The specific color of that light depends on which elements are present, like copper burning green or sodium burning yellow. These rules governing molecular density and electron bonds are the hidden forces that determine whether life survives in a frozen lake or a material resists the passage of time. These same chemical rules apply to organic matter in unexpected ways. For example, bananas are actually naturally radioactive. They contain high levels of potassium, and a small percentage of that element exists as the isotope potassium-40. Because this version of the atom has a slightly different nuclear structure, it is unstable and undergoes radioactive decay. This decay is a natural part of our environment. Radiation is present in the air, the soil, and even within our own bodies, reminding us that the biological impact of chemistry depends entirely on the dosage and context. Inside you, millions of these chemical reactions are occurring every second. Your stomach maintains a precise concentration of hydrochloric acid to break down food, while your neurons use a careful balance of ions to transmit every thought and movement. The human body maintains these simultaneous reactions with a level of precision that rivals the most advanced industrial facilities on the planet. Every time you inhale, you are interacting with atoms that have existed for billions of years. The oxygen entering your lungs today has been recycled through the atmosphere for ages. These indestructible atoms are constantly cycled through the environment, traveling through oceans, being absorbed by forests, and moving through countless generations of living organisms. If we trace the history of these atoms back to their origin, we find they were forged long before the Earth itself was formed. Elements like the carbon in your DNA and the iron in your blood were created inside the cores of massive stars. Under extreme heat and pressure, lighter atoms were crushed together through nuclear fusion to create the heavier elements required for life. This image captures a supernova remnant, the aftermath of a star's death. When these stars explode, they scatter their newly forged elements across the universe, seeding the clouds of gas that eventually become new planets. The calcium in your bones and the iron in your blood trace their history directly back to these ancient stellar events. We are a physical part of the universe that is now capable of observing its own history. From the carbon in a pencil to the iron in your veins, chemistry connects the mundane to the cosmic. Let me know in the comments which of these 10 facts changed your perspective the most. Chemistry is more than a classroom subject. It is the underlying language of everything we can see, touch, and breathe. Stay curious and keep exploring.